So good afternoon, everybody. Thanks for attending. We hope that we are going to give you something that's a little bit different, a little bit more visual, a little bit more entertaining. Ours is not quite as theoretical as what we've had in the past. Dash Engineering, we specialise in bearing failure analysis. So we've had a lot of, over the years, seen a lot of failures and different modes of failures, and there's a lot of methods that people think they know about that is the reason for failure, but it's not. So what we'd like to talk to you about today is grease-filled labyrinths as a sealing medium. Do we know whether they work or not? Has everybody here seen a grease-filled labyrinth? You know what I mean by a grease-filled labyrinth? Has anyone had any experience with grease-filled labyrinths? We're going to have to make this exciting then, because we're going to talk to you about grease-filled labyrinths. So in a nutshell, we've worked out why grease-filled labyrinths aren't reliable and why failures exist as a consequence. So what we'll talk about today is the types of labyrinths, some perceptions. Do these actually work? Because the perception is they do. And they've been in the industry for 60 years, and I'm going to knock you around a little bit and prove that they actually don't work. But it's not in the bearing manufacturer's interests or distributor's interests for it to work, because they don't get sales. So our data, we've done more in the last 13 years, just spherical roller bearing inspections of conveyor pulley failures, more than 1,000 of them. We know what's caused the problem. If we didn't, we'd be idiots. So Reece is going to share with you some of the information there. Then what we do, because we understand the problems, we can provide an engineered solution that mitigates the problem. So that's what Dash Engineering does. Who are we? We're Western Australian based. We have an East Coast division. There's 9 of us, and we would be, so 9 engineers, and we would be the largest bearing specialists in Australia. Group of bearing specialists that specialise in failure analysis in Australia. Today we're going to share with you some real-world industry experience and show you some real-world industry issues. What we do is provide solutions based on the root cause of the failure mode. So a little bit about us. We've got a lot of industry experience, steelworks. Mainly the iron ore industry is what we do in Western Australia, but certainly other industries such as power stations, food industries, grain terminals, that type of thing. These are the different types of labyrinths. You've probably seen them, you may not have seen them. Has anyone seen these different types? Throw me a bone. Just a little bone, no? So we've got our horizontal type labyrinth, vertical labyrinth, and they all use grease as a sealing medium. What we want to talk to you about today is how effective they are in actually stopping dirt getting in. Why are we discussing this topic? The reason that we want to share this with you or discuss this with you is because we do specialise in root cause bearing failure analysis, and we have seen that many failures of grease-filled labyrinths in plumber block housings in a number of different applications, mainly conveyor pulleys. That being said, if the clandestine people out there that haven't seen labyrinths work, we've seen opportunities where labyrinths do work, but the majority don't, and we can share with you why. A lot of the times in industry when grease-filled labyrinths fail, the bearings fail and they get given to us as a report to work out what the root cause was. There's a lot of perceptions, and people share a number of different ideas that they think it could be. Is it overloading? No, it's overloading. Is it false Brinelling? That's a good one. A little tiny line on the surface. Yep, there's your failure mode. Bearing quality. We've got an expert that talked about that today. Misalignment. Any excuse that they can come up with. Any excuse they can come up with to not blame what they sold you is the reason for failure. So what we found is the predominant cause of bearing failure in the conveyor industry is contamination ingress through the labyrinth seals. No doubt about it. On a Pareto chart, it would be 99%. The main bar on that chart. Did I skip a slide? No? So this is what we've seen. We've seen a bearing in a housing, and we end up with water, contamination, bad. So what we needed to understand was, why was this industry standard not working? This is what's on the SKF website. This is what is on the SKF website on how to do it. You put a sealed bearing in, which we've proven categorically is of no benefit. We fill it with grease in the housing here, and then we put our grease-filled labyrinth there, and they call it the 3-barrier solution. 3 barriers. Why do you need 3 barriers if you've got one that works? You've got a sealed bearing in there, then they're saying put extra grease in there, then they're putting a vertical labyrinth in there. And we see things like this. We see exactly the 3-barrier solution here. We've got our extra grease in the housing, which is a waste. We've got our sealed bearing, and we've got our labyrinth. Why, on the other side of the bearing, when the housing cap comes off, do we see this mud? And we haven't seen it once, we haven't seen it twice, we've seen it literally hundreds of times, and I sound like a sales rep in saying that. We have seen it hundreds of times. We have plenty of photographic and video evidence of it. We just want to share it with you so that you can at least understand what the process is. So I would like to go through this one specifically in a bit of detail with you, because this one was the initiation of what the process that Reece is going to talk with you about. We saw this over the years. So this photo was around about 2016. There's a group of photos after this, same ones, 2016. SKF sealed bearing, SKF extra grease in the housing, SKF vertical labyrinth. Why are we getting dirt from here that comes out through there, that comes out through there? Why? We carefully opened the stagnant grease. People say in industry, oh, the extra grease churns around, and it churns around in the housing and it keeps the lubricant moving through. No, it doesn't. There it is, doesn't move. As we get closer, you can see this grease has remained stagnant for so long it's discoloured on the outside, but fundamentally it's the same there, but something is happening at the shaft. At the shaft interface, there is movement. We wanted to understand why this was happening. We've seen it, and we've seen the chain of events that happens. This is just another photo. Same type of arrangement. We've got this distinct changing consistency of the grease, from the grease consistency to a yogurt type consistency when it gets mixed with water and iron ore dust. But it's got nothing to do with misalignment. Nothing whatsoever to do with it. It's that the grease-filled labyrinth doesn't work. We have seen this over and over again. So our customers asked us to come up with a solution. So what we'd like to share with the people that are interested is, at our booth, we have this engineered solution that has become a product because Rio Tinto and a number of the other iron ore mines in Australia are that happy with it that we've increased their mean time between failures significantly. Reece will go into that detail. This is raceway surface damage as a consequence of water. It's not overload. It's got nothing to do with that. It's contamination that's initiated this. And water within a bearing does create rapid surface degradation. We've seen that. We know it. We work with this. Some people would call it rubble. We call it information. We prefer it not to be rubble, but that's what we work with to get back to our root cause. And once we get this root cause, we can take away these myths and wives' tales and come up with an engineered solution to provide to your customers, our customers, based on real data, not perceptions and not what we think it should be. And we've had great success in that. So I'll hand it over to Reece, our senior engineer, and you'll be right.
button.
Middle button, I think. Yeah. Oh, you can go backwards and forwards, doesn't matter. You'll get it.
Hi guys, my name's Reece Morgan. I'm a senior mechanical engineer at Dash Engineering. I'm going to go into a bit more of the scientific outcomes of what we've seen practically. So as Dave explained, we work with predominantly heavy industry. So iron ore mining is our key client. We also work on the east coast of Australia with coal and everything in between. So large gearboxes, motors, a lot of conveyor pulleys and everything else that fails in Australia. So as Dave said, we've been around for 13 years. We've done literally thousands of conveyor pulley bearings, spherical rollers, mostly large sizes up to a 23188 and everything in between. The same deal with motors, gearboxes, exciters, everything like that. So we've got the data, we've got the practical data and experience of seeing these things. We attend the strip downs, we go, we take photos, we see all the dirt and water and the mud and the contamination that we've seen in previous slides. We already knew that there was a massive problem there. We knew the contamination was ingressing through the housing seals, but showing photos sometimes and just saying it doesn't get you a long way. What we need to do sometimes is prove things scientifically. So that's what we've set about doing. So we did this in 2 stages. In 2017, we were engaged by Rio Tinto while they were suffering big time on an overland conveyor system. These guys were running a 23 kilometre long conveyor. They were failing pulleys with 23188 size bearings within 6 months. These are 25 tonne pulleys costing 250,000 Australian dollars. And you can imagine the cost of downtime because of that, the cost of replacing that and the safety issues in doing that. It was taking them 3 days to change it. So they were suffering big time and they wanted something done about it. They tried all of the greasewood labyrinth type seals. They'd had enough and they engaged us to basically stop giving them the same report, which said dirt and water is your problem, and do something about it. So this is what we set about doing. So the first step was proving grease migration scientifically, somewhat. And to do this, we built a test rig. So we built this test rig basically where we can run 2 shafts continuously, and on that we can mount whatever type bearing housing seal we want. We can test it. We can test different conditions, different misalignments, different grease rates, all sorts of things. What we found in this initial testing was we basically proved what we'd seen practically. We proved that our theory of grease migration exists. And to do that, we basically just ran greasewood labyrinth type seals continuously. We relubricated them as per standard procedure. And what we found was that with standard grease-filled labyrinths, this is a horizontal example, with a V-lip as it comes from the factory. We ran this continuously for up to 50 days. And you can see here in the photos, quite interesting that while there was grease coming out the front, as you're supposed to see grease come out the front. That's the theory, the maintenance practice. You purge until you see clean grease out the front. There's also grease coming out the back and ingressing in the housing towards the bearing, and that's what's causing damage. It's what's causing wear, corrosive damage, and ultimately bearing failure very quickly. So this was quite a short time in operation. This was 30 days. You can see a little bit of grease coming out the back. 40 days, a little bit more, 50 days, and it's well on its way towards the bearing there. 50 days is not a long time. We want these things to last for 10 years or so. But after 50 days, you can see that potentially we've got contamination in our bearing already causing wear and damage. So this was 2017, and we did this as an industry white paper for Rio Tinto. From that, we had enough evidence to say that grease-filled labyrinths weren't working. They're not reliable. Whenever you use these types of seals, you can assume that you've got contamination in your bearing and that it's a ticking time bomb for poor reliability. It's going to fail eventually due to wear or due to corrosive damage, and you don't know when, you don't know how much contamination is in there, and there's not much you can do about it. So we wanted to get a better understanding of this, and to do that, just last year in 2024, we did a thesis study in collaboration with a West Australian university. Before I go into that, this is an example we quite often ask of our clients on mine sites when we get up there. is if you put a little speck of grease about halfway out on the diameter on a disc, just a stationary disc, and then you put another disc up to that one, and you rotate them slowly with respect to each other. Which way will that grease move? Will it move outside towards the outer diameter, or will it move in towards the center? Does anybody?
Is it going to go in? Is it going to go out? Who thinks it's going to go in?
Someone.
Someone. Who thinks that? So that means everyone thinks it's going to go out.
In or out? Green? You're right. And this is counterintuitive. A lot of people see that first up and they say centrifugal motion, it's going to fling it out. And that's the conventional nature of grease-filled labyrinth type seals, right? Especially a vertical type, is that the grease should go out and fling out, disappear, go to the environment, and your bearing should last. Wrong. The grease migrates in towards the center of rotation. And what we found was there's a phenomenon called the Weissenberg effect, which dictates this movement. So basically, because grease is a non-Newtonian fluid with viscoelastic properties, it behaves atypically when subjected to movement. So these were some of the preliminary testings. Basically, if you rotate a rod in a sample of grease, something strange happens. It will actually start forcing the grease inwards towards the rotating rod with such force that it will actually climb the rod, which is mind-boggling. It doesn't quite make sense in your head. What this also means is that with the rotating disc experiment, which I explained before, it's actually forcing the grease towards the center with enough force that it will actually start pressurizing the grease on the inside. And you can see this was spinning for 160 seconds on our test rig, and it was actually pushing a little sausage of grease out of that hole in the middle. This is also in our test rig. So I'll play this video. This is two very common types of grease-filled labyrinth type seals. On the left here, we've got a vertical labyrinth type seal. On the right, we've got a horizontal type labyrinth seal. The main difference is that the labyrinth fingers on a vertical are vertical like that and horizontal like that. It's not there. Can we play the video on this? Do you have control of that? Yeah. Oh. Oh no. Oh, okay. This was a video in the presentation we sent. It is a video. It goes for about a minute. It was. No, not easily. That's all right. I'll describe it. Yeah, bugger. This was a video. This was a time lapse of images we took on our test rig. So
what we can do is run it on your computer at our booth. We'll show you that because it's the key. So you'll explain.
Yeah. So we'll talk about that. We ran this continuously. We injected grease into the seals as per normal grease rates, running it at 70 RPM. And I've got a little comment down there. This only took 33 hours, but you don't see the end result. Please come and see us at our booth and we will show you the video. It is quite astonishing. Basically, what is happening is normal maintenance convention is you inject grease into that grease nipple there and you will see, dirty grease come out of the outside first. Then you'll see clean grease. Then you'll say your seal's clean, your bearing's safe, it's clean, everything's good. That's maintenance practice. Doesn't happen that way. So what we saw on this one, and I'm giving away the video, but please still come and watch it, is the grease is actually forced from the outside of this one inside the seal. It jumps the little V-lip that is in there, and the grease will actually start migrating, just like the photos previously, along the shaft, up and over that lock nut and straight into the bearing. And in 33 hours, the end of the video will show there's actually a substantial amount of grease at the lock nut about to enter that bearing. what we see in the real world, this is a controlled environment with clean grease. In the real world, that would be dirty grease, and it would be carrying iron ore, abrasive coal, water, whatever that bearing is exposed to. A little bit more of the workings behind it. So basically what is happening is the rotation of the shaft is causing a energy gradient, and what happens is towards the outer diameter of the seal geometry, you're getting a high energy state, towards the inside a low energy state, and basically that creates a force that is forever pushing grease towards the inside of the shaft. What that means inside a vertical labyrinth type seal is where you've got green arrows here, where you've got the horizontal geometry, basically two rotating cylinders, it's pushing grease both ways equally and oppositely. Where you've got vertical geometry, just like the spinning disc example, it's pushing grease exclusively inwards and only inwards. So you can see the net result is that any grease that's on the outside is going to eventually make its way towards the inside. And this is a standard seal design. They are literally pumping grease from the outside in and carrying all sorts of contamination with them. So we've got all this knowledge now. So we've got this proven scientifically. We've got the photos to show that it is actually happening out there in the real world. As I said, we've got thousands of examples of failed bearings because of contamination ingress via these types of seals. So what have we done about it? By understanding the forces behind grease migration, how it moves, why it moves, and what we can do about it, we can now provide our clients with bespoke engineered solutions applying this knowledge. So our clients come to us, we do the failure analysis, we look at their bearings in the practical sense of where they're operating, how they're operating, what the cause of failure is and what they can potentially do about it. A lot of the time, because we are working in horrendous environments in mining, it is a contamination issue. We see abrasive wear or corrosive damage or a combination of both. So what we can do is design bespoke sealing arrangements for their machines, basically replacing vertical labyrinth type seals with bespoke geometry made to suit that machine. So we design these types of seals in-house. These are real examples that we have designed, built and put out into industry on machines. We also were challenged to solve the issue for Rio Tinto that started all of this was conveyor pulley bearings failing, causing all sorts of costly downtime and untold grief. So the results of the first testing that proved the grease migration theory existed was we were challenged to come up with an engineered solution housing seal to prevent contamination ingress. And this is our SAPO seal. So this was designed, as I said, as an engineered solution for a single problem, was these big pulleys failing, causing millions of dollars of downtime. What we set out to do with this was come up with a seal with no excuses, right? We want this thing to work. We want to live by the sword and die by the sword. So we put it all on the line. So the excuses for poor seal performance, as I've explained in great detail, are if we're using grease in labyrinth type seals, we've automatically got grease pumping in with contamination. Other excuses in the industry were misalignment. So I think one of the specs on a quite a common design in Australia was you need to align this thing within 0.35 of a degree on a conveyor pulley. This is a 20-ton conveyor pulley. It's got no good datum points. It's got footings that are out of alignment, bent, whatever. It's hanging from a crane. We're not getting that alignment, right? And we're not measuring it, and we certainly can't sign off on that. So there's your excuse for poor reliability. We also gave it the ability to be monitorable and maintainable. So our clients can actually take an active approach to ensuring the reliability of their assets on this. Without going into too much detail, and please come and see us at the stand to know the workings of how the seal works. But basically, we use a closed oil system on this one where we can flush, sample, check, maintain it, and do a reliability check on the go. We've been developing these and rolling them out on Rio Tinto and other iron ore mining companies in Australia for about seven years now, and having fantastic success. This is a variant of the SAPO seal, which we've developed quite recently as well, and we understand that grease has its limitations as a sealing medium, right? We know that it flows in certain ways, it's a bit clumsy, it behaves atypically. But we also understand that it is so ingrained within industry that it is not going to change anytime soon. We're so geared towards pumping grease into our bearings and our seals. That's what we're set up for. It's not going to change. So we have a version of the SAPO seal which is optimised knowing what we know about grease migration and misalignment and all of the real world limitations of sealing in mining applications. And we've come up with the G series SAPO seal, which is the same functionality as the original SAPO seal, designed with no excuses, but made for more of a generic application where you can you hook it up to your conventional lube systems and maintain it as per you would have done on your greasewood labyrinth type seal. So the results of these solutions have been quite astounding, and I think that's because we are the only people doing this. So we're competing with bearing suppliers who are selling the bearings, the housings, and all of that stuff. We only sell these engineered solutions. We want them to work. So we've done quite a few bespoke designs for all sorts of machinery, gearboxes, exciters, crushers, even motors, things like that. The original SAPO seal, we've calculated that we've saved Rio Tinto in Australia $7.8 million in just avoiding conveyor pulley failures. That's not accounting for the cost of unplanned downtime, the cost of safety, cost of all sorts of other downstream issues. That is just in avoiding rebuilding that pulley because of a bearing failure. We've also got the new G series taconite SAPO version as standard on these mining companies. So again, Rio Tinto is fitting these as standard on their conveyor pulleys. We're also rolling them out across other mining companies and other mining types. So coal mining on the east coast of Australia, iron ore, all sorts. Anything else to add? So yeah, thank you for your attention. It's been a pleasure. Please come and see us at our stand. We've got so much to show you. We can show you the seal, how it works. We'd love to show you the video. It is quite astounding how inefficient greasefield labyrinth type seals are at sealing our bearings from contamination in harsh environments. Thank you.
Thanks, Rob.